From Merriam-Webster, the third definition out of 5 for induction reads, mathematical demonstration of the validity of a law concerning all the positive integers by proving that it holds true for integer 1 and that it holds for an arbitrarily chosen positive integer k, it must hold for the integer k plus 1, also called... No wonder students don't want to learn about mathematical induction. That sounds awful! I know that we have talked about a number of methods of proofs in previous videos, but I've got one more to talk to you about. Proof by induction. Now, this is one of my favorites, and it's probably because it mimics the architecture of our programs, of a loop in our program. You start out with an initial condition, and then you increment some sort of a counter and go through. And we need to make sure that this structure is a working structure. Now, it kind of works by that idea of an example. You know, if you try something for your particular algorithm, if it works for that example, then we build off of that. Now, I did tell you that trying to prove something by showing that a single example works is not a valid way of proof. For example, saying that 2 squared equals 4 is no way of saying that all powers of 2 are even numbers. But if you prove an initial case is true and then show that incremental cases are true, then the algorithm is true. Let's go ahead and talk about the process. So let's look at this as some sort of a number line, all right? And at this base, at this starting point, we have this thing called a basis, which I'm going to represent with B. Now, it's the starting point, and typically the starting point is, well, it's typically 0 or 1, you know? It's a good place to start counting from, right? Now, what the point is that we are going to prove, and this is step 1, prove P of B is true, all right? And remember, P of N is a proposition. A proposition that changes based on different values of n. So for example, I could have a proposition that n is greater than 5. And for different values of n, we get a true or false coming out of our proposition. So the idea is to start out our proof by showing that for b, that P of b, or you know, that when you put b, substitute b for n, that is true, that proposition is true. So we've got a starting point. All right. Now, the next thing that we do is we assume P of K is true. And this is where things get a little funky. What you're looking at is saying, okay, let's assume that for some K, and I'm not defining K, I'm not saying K is equal to 5, I'm saying that for some random K that we're not defining, go ahead and assume it's true. And then, based on that assumption, prove that P of K plus 1 is true. And so you're taking an increment. So you're incrementing by 1. So why does this work? And once you were able to assume P of K is true, and then prove that PK plus 1 is true, then what you've done is actually said that everything is true. Because you could assume that K is equal to B. I mean, I told you, don't define what K is equal to. You could assume that K is equal to B. And by assuming K is equal to B, then you've proved, because you did this proof, that B plus 1 is true. And then you can say, well, K is equal to B plus 1. And that will prove that B plus 2 is true. And then you substitute B plus 2 for K, and that shows, because of this proof, that B plus 3 is true. And do that ad infinitum, you've got the entire range from B up proven to be true. Just like you can't know how to drive a car simply by sitting in a class and learning how a car is driven, just showing how a proof by induction works is not enough to show you how to do it. So we're going to go through a couple of examples here. Now I'm going to start out, I'm going to create something. I'm going to do a grid of n by n squares, all right? So I'm creating this grid of n by n squares. And what I'm going to do is I'm going to color the upper right half above a diagonal. What the heck does that mean? Well, let's start out. Let's start out and assume n is equal to 1. All right? Now I've colored in exactly 1 square because I'm looking at this idea of a diagonal is cutting through this grid, and any square that exists in that diagonal fully or partially gets colored in. So how many colored squares do I have? Well, I have 1 square colored, right? Now, let's increase the size of this to a 2 by 2. We're going to make n equal to 2. And the diagonal runs through this way, so that means that these 2 squares are now also included. So n equals 2. We have a 2 by 2, and that means I have 1, 2, 3 squares colored. All right? Now, let's increase this a little bit more. All right? And now my diagonal runs through these squares, and so I have n equals 3. It's a 3 by 3 grid. I have 1, 2, 3, 4, 5, 6. So I have 6 squares colored. All right? And in fact, let's keep going on and on and on. And what ends up happening is you get to some point where you have, and I probably should make that a little less. There we go. All right, and we'll kind of make this diagonal go here. I don't know how well this drawing is going to work, but now I have some random n by n square of grid, where the upper diagonal is all colored in, right? And so I've got some of these uncolored, some of them colored. And so for P of n, what is it going to have? How many squares? Now, let's talk a little bit about how we're forming this. Every time we add another row, so we went from 1 square, we had n equals 1, we had exactly 1 square added, 1 square colored in. When we went to n equals 2, when you added that top row, n equals 2, we added 2 more colored squares. So you had just this square, added another row of 2, you added 2 more, right? And then when we went to n equals 3, so the block like this, we had 3 rows. When we added that 3rd row, we added 3 colored squares. When you add the 4th row, you add 4 colored squares. So actually, what we are looking at is this idea of 1 plus 2 plus 3 plus 4 all the way up until you add n. That is going to identify the number of colored squares that we have. Wouldn't it be cool if we could come up with just a general equation instead of having to go through and adding this sequence? So when we add the 9th row, I have to figure out how many squares are colored for the 8th row, then add 9 to it. And then to the 10th row, we figure out how many squares are for the 9th row, or excuse me, how many squares are colored for a 9 by 9 and add 10 to it. You know, that's probably not the most efficient way to do it. So what we're looking for is an equation that expresses this. Well, the way we can solve this problem is that if you look, I have the upper diagonal colored so that there's just a few more of the colored squares than there are of the non-colored squares. So what we're going to do is we are actually going to change the dimensions just for the purpose of a proof. We are going to add another column here, all right? And so we've added this additional column, and we're not going to color anything in it. And look at it this way. I have the full n squares uncolored, n minus 1, all the way down until we have 1 uncolored square, just like we have 1 colored square all the way up until n colored squares. So at this point, I've got exactly as many colored squares as I have uncolored squares. Well, what's the size of this grid? So I've got n rows by, and sorry about this pen. Let's see if we can get this a little bit darker. By n plus 1 columns. All right? So we just simply added another column, didn't shade anything in. Now exactly half of our squares are shaded, half are unshaded. I have n plus 1 columns and rows. How many grids do I have? Well, that's pretty easy, right? It's n times n plus 1. How many of them are shaded? Exactly half of them, all right? So I got this idea of 1 plus 2 plus 3 plus 4, all the way up to adding in n. I actually have an expression that might represent that sequence. How do I know if that's actually true? I mean, I kind of showed how it works, but let's prove that it's true. So what we're proposing is that 1 plus 2 plus 3 plus all the way up to n is equal to n times n plus 1 over 2. All right? That is our proposition. Is it true for every n? So that is our proposition. All right, so we have P of n. That's our proposition. So how do we prove this? Well, the very first thing, remember, the first step was to prove basis, to prove that this is true for the basis. And in our case, our basis, b, is equal to 1. So this becomes 1, and 1 added all the way up to n is just 1, is equal to 1 times, and 1 plus 1 is 2, divided by 2. Well, that's equal to 1. I'll be darned. It works. Now, that's all you need to do. You just need to prove it for the basis. But you know, sometimes I like to prove it for a few more just to make myself, well, it makes me feel a little bit better to see, oh yeah, this is working. But it also kind of gives me a little bit of a better feel for how I'm going to do the second part of the proof. So let's go ahead and prove it. This was for n equals 1. Let's figure out what it is for n equals 2. So this is 1 plus 2 equals 3, which is equal to, and then let's see what happens on this side. So that was the left side of the equal sign. Let's see what happens on the right side of the equal sign. That is 2 times 3 divided by 2, which is equal to 3. How many bricks was it? 3. Remember how many blocks were filled in our grid? So 3 equals 3. So it works. Let's just do one more. All right, let's do n equals 3. This is 1 plus 2 plus 3 equals, well, that's 6, is equal to, let's do the right-hand side of the expression. This is 3 times 4, right? 3 times 4 divided by 2. Well, that's 12 divided by 2. It's 6. You feel good about it now? All right, so there was the first step, proving that it worked for the basis. Let's do the next one. Now, step 2 says, assume that P of n is true for n equals k, for some k. So what does that mean? That means that we're assuming that 1 plus 2 plus 3 all the way up to plus k is equal to k times k plus 1 divided by 2. We're just saying, let's assume that that is true. Is it true? What I would like to do or propose is we go ahead and try and solve this for k plus 1. So I've got P of k plus 1, right? And that is 1 plus 2 plus 3 plus all the way up to k plus 1, right? We're just adding the next integer. Now this bit right here, that look familiar? Well, yeah, that's P of k. And so what we're saying is we assumed that this was true. Therefore, this, we can simply substitute this value in. And so let's go ahead and substitute the 1 plus 2 plus 3 all the way up to just k. That bit right there, substitute it for what we assumed to be true. So that becomes k times k plus 1 divided by 2 plus k plus 1. All we're doing right now is we're just doing this proposition. We're doing the left-hand side of the expression for k plus 1. And using our assumption, we're going to see if we can work to the right-hand side of the expression. So how would you solve this? Well, it'd be nice if we could make it all one fraction, right? And so to make a common denominator, what I'm going to do is I'm simply going to multiply the k plus 1 times 2. And so we got k times k plus 1 plus, and then 2 times k is 2k, and then 2 times 1 is 2, and have that all divided by 2. All right. Next, I can multiply this all out. And what I get is this will be equal to k squared plus k plus 2k plus 2. And that is all divided by 2. Carry our denominator along, right? I can simplify this a little bit, right? You see the 2k plus the k, those we can add together, and you've got k squared plus 3k plus 2 over 2. Wow, here comes one of those quadratic equations that we have to factor. Turns out that this quadratic equation factors to just k plus 2 times k plus 1 divided by 2. All right, because k times k is k squared, k times 1 plus k times 2 is equal to 3k, and then 2 times 1 is equal to 2. So there you go. That help us? Did that finish it? Well, I ran out of room here on the board, but notice that that can be written k plus 1, right? K plus 1 times k plus 1 plus 1, right? I just take that 2 and turn it into 1 plus 1. How does that help? Well, what happens if I put parentheses around this? And what I'm showing is that for k plus 1, substituted for n, you have k plus 1 times k plus 1 plus 1 over 2. Going back to the original equation. And so I showed, assuming that pk is true, then we wrote down pk plus 1, and using the assumption, we worked our way down to show that this is true for k plus 1. Something odd was noticed when it came to the squares of integers. Let's talk about n. We've got, how about 1, 2, 3, 4, 5, 6, 7, 8, 9. Heck, we'll leave it there. N squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared 16. Then we have 25, 36, 49, 64, and 81. All right, you buy that? I don't think I made any mistakes. Might have. Send me a note. Let's look at something. How about the difference between n squared minus n minus 1 squared? In other words, what I'm going to do is I'm going to take one of the squares and subtract from it the square that came before it. And what that gives us is, let's see, 4 minus, and we don't have anything below that. I mean, you could do 0 squared, I guess, but 4 minus 1 is 3. 9 minus 4 is 5. 16 minus 9 is 7. 25 minus 6 is 9. 36 minus 25 is 11. 49 minus 36 is 13, 64 minus 49 is 15, and then 81 minus 64 is 17. Notice anything? Yeah, we kind of noticed something, right? These are the odd integers. 3, 5, 7, 9, 11, 13, 15, 17. Wow. That means that we could actually figure out what the square of something is by adding all the odd integers. Let me go ahead and try and write that in a formula. I could say that 1, and this is our proposition, P of n, right? 1 plus 3 plus 5 plus all the way up to 2n minus 1. Remember, 2n minus 1, that is a way for us to represent an odd number. So we're adding together all the odd numbers up to 2 times n minus 1. What does that equal? Well, it turns out that equals n squared. Now, I've shown that it works for the first 9, but that doesn't mean it works ad infinitum. It doesn't mean that it works for all of our integers. So, what was step 1? Step 1 said, prove true for the basis, right? And what was our basis? That PB, that was B equals, well, let's just use 1, all right? Now, the way this works is we've got what? 1 add it all the way up to 2n minus 1, so 1, is equal to 1 squared, which equals 1. That worked, right? Now, like I said before, you only need to prove it for the basis. Once you prove it for the basis, you're good above that. But, like I said, I like to get a feel for how this is going, what direction this is taking, by doing a couple of more. So this was for n equals 1. What does it look like for n equals 2? Well, we've got 1 plus, and then it goes up to 2 times 2, that's 4, minus 1, 3, that's it, we're done. So that's equal to 4, which is equal to what? Well, turns out 2 squared. It works. Want to do one more? Let's go ahead and do n equals 3. That would be 1 plus 3 plus 5, which is equal to 1 plus 3 is equal to 4 plus 5 is equal to 9, which is equal to 3 squared. So it turns out, at least for these first three, it works just fine. What's step 2? Well, step 2 says, let's assume that it is true for n equals k. So, assume, and this is step 2, assume p of k is true. What does that mean? That means that 1 plus 3 plus 5 plus all the way up to 2k minus 1 equals k squared. So now that we've made our assumption, what I like to do is start on this left side of the expression and work my way, based on this assumption, to the right side of the expression. So we're going to go ahead and say that this pk plus 1 is 1 plus 3 plus 5 plus all the way up to, and I'm going to go ahead and include the 2k minus 1, but then I'm going to also add the 2k plus 1 minus 1. Notice my parentheses, because what I'm doing is I'm going to substitute for this k, the k plus 1. All right? Now, how exactly are we going to work this out? Well, this guy, remember, I can also say that we've already made the assumption that that's true, and I've got k squared, right? And so I can just substitute this bit right here for k squared and get 2k plus 1 minus 1, right? All right. I guess what I could do is I could multiply that out into its different elements, right? And so I can get k squared plus, and then get 2k plus 2 minus 1, right? Hopefully I multiplied that through, got 2k plus 2, that bit right there, and then tagged along the minus 1. I simplify this, I get k squared plus 2k plus 1, so 2 minus 1 is just 1. Guess what? That factors, and it factors into k plus 1 times k plus 1, which is equal to k plus 1 squared. K plus 1 squared, that's the other side of this proposition. We've proved it true. Before I release you out into the wild to do inductive proofs on your own, let's do one more example. Some of you are very familiar with this idea of base 2 or binary, right? And you're probably familiar with the idea that, oh, I don't know, if we've got these, let's just say we have 4 binary positions, 4 binary digits, bits. And we have the 2 to the 0 place, which is equal to 1. 2 to the 1 place was equal to 2. 2 to the 2, which is equal to 4. And then 2 to the 3, which is equal to 8. And so if I have 1s in all 4 of those positions, I have 8 plus 4 plus 2 plus 1, which is 15. If I add 1 to this, what it does is it adds 1 by changing all these bits to 0 and putting a 1 in the next position, which is the 2 to the 4th position. So what we're saying is 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3. You add 1 to that, you get 2 to the next position, a 1 in that position and zeros everywhere else. Let's try writing that in a mathematical expression. What we're saying is 2 to the 0 plus 2 to the 1, and that kind of looks like a 6, doesn't it? 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus all the way up to 2 to the n, this is our proposition based on n, is equal to 2 to the n plus 1 minus 1. Pretty basic binary stuff. If you've hung around binary very long, you've seen this expression. But can we prove that it's true regardless of how many bits we've got? Well, let's start out with the base case. Remember our step 1. And what we're going to do is have our base case just simply be 0. All right, so that means 2 to the 0, right? We've got this n equal to 0. So that says 2 to the 0 is equal to 2 to the, and that'd be 0 plus 1, which is equal to 1, minus 1. So 2 to the 0, that's equal to 1. 2 to the 1, that's equal to 2, minus 1, which is equal to 1. So we've proved it for the base case. So where do we go from here? Step 2. Well, step 2 says assume P of k is true. And what that's telling us is that 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus all the way up to 2 to the k is equal to 2 to the k plus 1 minus 1. We're assuming that that is true. Now what we need to do is prove p k plus 1 is true. How does that work? Well, 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus all the way up. And I'm going to go ahead and say 2 to the k plus 2 to the k plus 1. That's our left side of the expression. What does it look like on the right side? Can we work this, based on this assumption, can we work this to the right side of the expression? Well, what we've done before is just simply taken the ones for the pk, and we've just said, okay, we've assumed that this is true. And what you've got is 2 to the k plus 1 minus 1 plus then this 2k plus 1 that's sitting there, right? And what do we do from here? Well, if you look at this, remember, all I did was just say, okay, this bit right here is this bit right here. And so I substituted this right here with this. And so I took the 2 to the k plus 1 minus 1, that's right there, but I didn't substitute the entire expression. I still had this plus 2k plus 1 hanging over, so I just brought that in. Now notice I have 2k plus 1 minus 1 plus 2k plus 1. So there are actually two 2k plus 1s. Well, that's just equal to 2 times 2k plus 1 minus 1, right? Well, what happens if I multiply 2 times 2 to some exponent? Well, I increase the exponent by 1, and that becomes 2 to the k plus 1 minus 1. Well, 2 to the k plus 1, isn't that really our 2 to the k plus 1? Isn't that our expression over here, 2 to the n plus 1, where k plus 1 has been substituted in? So what we show is that I've got 2 to the k plus 1 minus 1 is equal to 2 to the 0 added up all the way, all the powers of 2 added up all the way to 2 to the k plus 1, and we've proven it true. All right? Okay, so there you go. Proof by induction. May seem a little complicated. No. Coming up with this first step, not complicated. However, deriving the left side of our equation from the right side of our equation based on the assumption that it works for k, but we need to derive it for k plus 1, hey, it just takes some practice, and we got plenty of problems we can practice on.